Hi everyone, this is Professor Mankowski and welcome to MAT150. In this video, we're going to do an introduction to Chapter 7, Confidence Intervals, and in some books it might be referred to as estimation. So we're going to go ahead and bring up our presentation screen. Okay, and Chapter 7 is going to begin with a bit of an afterthought of where Chapter 6 was. In Chapter 6, we found out that if somebody gives us information about a population, in particular what the population average mu is and what the standard deviation sigma is, we can use that information to go and assess the probability of what a sample average is going to be, or what a sample average is going to do that we take from the population. So in particular, we're talking about gauging the probability of the sample average, X bar. So how do we do that? And the answer is we use the central limit theorem, which is something that we learned how to do in Chapter 6. Now, while it sounds really great on paper, all of a sudden we say, well, hold on a second. In real life, we're never really going to know anything about the population. So why are we assuming that we're going to know sigma and we're going to know mu? So statisticians were thinking about that and they said, well, this is kind of true. So what do we do? And they came up with this bright idea and they said, if the central limit theorem can help you take a population, take information from the population and learn about the sample, maybe it'll go backwards because we can always draw a sample from a population. So what we do in Chapter 7 is we learn how to make generalizations about what we're seeing in the sample to teach us more about what's happening in the population. So we can get approximates for mu and that we can get approximates for sigma. So we're going to go ahead and begin with an introduction to Chapter 7. And we're going to use an example about approval ratings, presidential election. Now, picture like this. Presidential election is 4 weeks away and Joe Biden has a statistician on hand. I'm going to use Joe Biden for no particular reason. And Joe Biden says to the statistician, I want you to go ahead and figure out what my approval rating is. So that statistician does their calculation and their study, and they find out that the approval rating is 52%. And this looks like a pretty good approval rating because 52% is more than the majority. That's enough to win the election. If the statistician gives that information to Joe Biden is going to turn around and he's going to say to the statistician, you're fired. Now, why is Joe Biden going to fire the statistician? The reason is because it's very, very risky to rely on just one number, what we call a point estimate, to tell us what we need to know about the national approval rating. Let's take a look at what happens when we make an interval out of this percentage. It goes from a low end of 48% to a high end of 54%. If Joe Biden is up there on the high end at 54%, he's in pretty good shape because that's enough to win the election. However, if he's down at the low end, 48%, that's not very good because it's not enough to win the presidential election. And if Joe Biden's down at 48%, it means he still has a lot of work to do. So our big takeaway is that we are going to learn how to use intervals to estimate what we need to know about the population because it's less risky. And what we're going to do is we're going to start with an important feature that we want to review in the bell curve that has to do with how to find z-scores that correspond to area in the tails of our bell curve. And once we've had a chance to review that, we're going to go ahead and we're going to start section 7-1. So if the presidential election, we're going to say it's 4 weeks away, and Joe Biden says to the statistician, I need you to estimate my approval rating and I need you to be 90% accurate. So first thing that we're going to do is we're going to calculate something called alpha. And alpha is going to be the area left in both of our tails. Because we've already shaded 90% of the area in the middle of the curve, and we know that the total area under the whole entire curve is 100%, we can take 1 minus 0.9 to find our alpha, and that's going to equal 10%. Now, what we want to do is we want to narrow this down to how much area is in each individual tail. So we can do that by taking alpha, dividing it by 2, and it's going to tell us that 5% of our area is in each tail. Our job now is we need to find what's the z-value that's going to correspond to that 5%. And we'll work with the low side of the tail first, the low side of the curve first. So we're going to go ahead and label both of the tails are 5%, and we're going to track down the left side. So if we get our z-table out and we identify the closest area on that table that comes to 5%, it's going to let us know that our z-scores are going to be plus and minus 1.65. So now the election's getting a little bit closer. Now the election's 2 weeks away, and Joe Biden says 90% accuracy isn't good enough. I need you to estimate the approval rating, but be 95% accurate this time. So we're going to calculate our alpha once again, and our alpha for both tails is going to be found by doing the same thing we did before. 1 minus 0.95 is 0.05, and we want to capture the area in each individual tail again. So we're going to take the alpha divided by 2, and it's going to be 0.025. We're going to go ahead and find the z-score that matches that 2.5%, and it's going to tell us that the left side is going to be negative 1.96, the right side will be positive 1.96. So now it's the night before the election, and Joe Biden says, I need to know everything, give me 100% accuracy. And the statistician says, well, I'm not going to do 100%, but I'll give you 99%. So we find the new alpha. Our alpha is going to be 0.01. We divide it by 2, and it's going to be 0.005. We're going to go into our z-table, and it's going to turn out that our z value on the left side is going to be minus 2.58, and on the right side is going to be positive 2.58. So when we get into the introduction now for chapter 7, we're going to end up learning how to estimate all kinds of different population parameters, averages, proportions, standard deviations, variances. And section 7.1 is more specifically about estimating population averages. So what we're going to do is we're going to use an example here of we have a friend, and they're going to come and visit us. And they know that we work all day long, so while they visit us and stay with us, they ask to use our vehicle. And we tell them, you can use our vehicle while we are at work. We would just like you to replace the gasoline that you've used. And your friend says, okay, well, that sounds fair. How much is gasoline? And we want to impress our friend with our MAT150 class. So we go ahead, maybe sample the prices at 40 different gasoline stations. And we find out that the average price of gasoline is $2.25. We would call that $2.25 a point estimate. And that is using one number to stand for the population average. We know, though, that whatever gas station our friend drives into, it's probably not going to be exactly $2.25. So we're going to give or take 10 cents. And we're going to call the give or take 10 cents error. So from this information, our friend can infer an interval between a minimum number and a maximum number that they expect to pay. $2.25 minus 10 cents will give us the low end. $2.25 will give us the high end, the $2.35. So now what we're going to do is use the same idea here to introduce our way into the mechanics for the formula we'll use for estimating population averages. We're going to use something very similar to what we just did to estimate the average. We're going to use our point estimate and add and subtract what we call error. So our point estimate is going to be our sample average, and the error is going to be this component here. And I know it looks a little peculiar. The purple part of that formula is coming from the standard deviation that we had seen applicable in the central limit theorem. We found out that if we're working with the distribution of sample averages, which we are, the standard deviation of the distribution of sample averages is equal to the population standard deviation divided by the square root of n. And in our central limit theorem formula, we recognize that component as being in the denominator. Our Z alpha over 2 piece of the formula is going to come from the Z-score that's applicable to the tail regions of the bell curve that we were just learning how to use and review. Now, at the end of the day, if all that seems overwhelming, all you have to remember is that your formula is going to be your point estimate of X bar plus or minus this error piece. The good news is most of this formula is just going to be numbers that plug in straight from the question. And the part that's going to be tricky, if anything, will be trying to figure out what that Z-score is going to be. So if you're wanting to practice how you get that Z-score, a great place to go to look is on page 366, number 9. Practice going through A and E and make sure you're able to match the Z-score for each of those confidence levels that they offer. Okay, so now what we're going to do is we're going to go through a practice exercise to see how we're going to get our formula and put it into action. So pause the video and read through the question, take a few minutes. Okay, so in this question, it looks like what's happening is somebody wants to figure out if they're going to open a daycare center, how much money should they charge, which is probably a pretty good thing to figure out. So to get that answer, they go through a sample of 50 different 4-year-olds that are in daycare centers, and they compile some information from that sample. We need to use the information from that sample to generate a confidence interval estimate of the population average. So what we're going to do is we're going to start just by writing down all the numbers that they gave us in the question. When we look inside the question, the first number they gave us was the number 50. And they seem to be talking about 50 subjects that were studied to capture the data. So it's probably true that 50 is going to be our sample size. Now, the next number they gave us was 3,987, which was an average. And we know that there's two averages. There's a population average mu and a sample average X bar. So how do you know for sure which one it is? But it's probably not the population average because that's what we're trying to estimate. And the way to be completely sure is we notice that that is connected to the information we received when we were looking at the sample size. So that's enough to let us know that 3,987 is going to be our X bar. The next number they gave us was identified as the population standard deviation, 630. So we're going to go ahead and we're going to mark sigma at the 630 spot. The 90% confidence is going to be our Z alpha over 2 value. And from what we had seen in the prior videos, we're going to go ahead, or rather in the prior part of this video, we're going to assign that a value of plus and minus 1.65. And now that we have all this information, we're ready to start working on filling in our formula. As we have all our numbers attached to different symbols. So we're going to go ahead and we're going to start to put the components into the formula pieces here. And the low side is going to look just like this. Low side is going to come out to be $3,840. To get the high side, we're going to use exactly the same formula expression. The only difference is we're going to be switching the formula to read a positive instead of a negative. That positive sign is then going to account for the positive Z-score that we had on the right side of the bell curve. So when we fill this in, we're going to end up with, on the high side, $4,134. So to summarize everything that we found out, we're going to say we're 90% confident that the yearly tuition is between $3,840 and $4,134. They also asked us in the question, what would be a good amount of tuition to charge if we want to stay competitive? And if we want to stay competitive, that probably means we want to gravitate towards the low side of the interval. So we would say somewhere around $3,840 is what we would like to charge. Now, let's go ahead and let's take a look at another sample question. Okay, so our next example here. Pause the video if you'd like to take a minute or two, read through the question. Okay, so inside of the question, it looks like we're estimating how many hours of television a kindergartner is watching. And we have some information on a sample that we've taken to help put together all the information we're going to need for our confidence interval formula. So we're going to start the same way we did before, by writing down all the numbers that they've given us from the question. And we're going to go and identify what's what inside of the paragraphs here. And the first thing they did was mention that 415 subjects were used for the study. So the 415 sounds like it's the sample size. We're going to go ahead and label the 415 hour N. And the next thing they told us was that an average was 5,000 hours. Because that 5,000 is connected to the information about the sample size, it looks like our 5,000 is going to be our sample average X bar. And the next number we have, 900, is mentioned in the context of the standard deviation of the population, and that lets us know that 900 is going to be our sigma value. Now, the very next number, 4,000, does not really seem to be connected to the question. In fact, or rather, it doesn't seem to be connected to the sample. So it looks like it's actually not going to be used for our formula. It's going to be information that comes in later on during an evaluation stage of our answer. So for right now, we're just going to cross out the 4,000. And the 95% is going to be used for our Z alpha over 2 value. And we can go ahead and mark in that's going to be plus or minus 1.96. So now we have nearly everything that we need to do to go ahead and start to fill out our confidence interval formula. So we're going to write our formula back on the screen. And when we fill it out, for the low side, we're going to end up with 4,913. The high side, once again, will be exactly the same, except the minus sign is going to switch with the positive sign. And we're going to end up with 5,087. So we could say that we're 95% sure that the kindergartners are watching in between 4,913 and 5,087 hours of television. The last thing that they mentioned in the question was that part about the 4,000. They said a parent claimed that their child was watching 4,000 hours, or if a parent claimed that their child was watching 4,000 hours, would that be believable? If we take a look at how 4,000 compares to our interval, it looks like 4,000 is very far below the minimum on our interval. So we would say it probably doesn't look believable because 4,000 is so far out of the interval. So when we've been reading through our questions, especially the last one, let's take a minute to talk about the sample size that we used. When we had seen 415 kindergartners were used, one thing we never really talked about was how did they know to use exactly 415 kindergartners? When we were looking at the question about daycare, they did a sample of 54-year-olds. And how did they know that the exact number was 50? We kind of say, time out. How did they know that it shouldn't be 51 or 49, but exactly 50? There's another question, number 15. They are doing an estimation and the sample size was 35. So how did they know that exactly 35 people should be used? Question number 13, they used 50 workers in that sample, a sample size of 50. And there again, brings us back to between a 415, our 50, our 35, and the 50. How do you know what your sample size should be? We would love the sample to be as large as we can, take the whole entire population for our sample, but obviously we can't really do that because we have limitations. We're limited by things like money and time and staff. So what happens is we have to know what's the minimum that we can do in a sample to meet our needs for the confidence level. So there is a special part of our formula we can use to figure out exactly what the minimum sample size should be. What we're going to do is we're going to take a look at just the right side of our confidence interval formula. And the right side we're going to call the error. So what's going to turn out to be the case is we have 3 terms. Each of those 3 terms are indicated with arrows. And if we have our confidence level percent, we have our sigma, we have an error that's already told to us as part of given information, technically we should be able to use all those bits of information to figure out what's going to be a sample size. In particular, what's going to be the sample size to create an interval estimate at a certain level of confidence for a certain error. So how do you do all that? How would you actually algebraically solve for n? And the answer is, if we take our error equal to the configuration we had just seen on the last screen, we can algebraically rearrange it to solve for n. And this is going to be what we call our minimum sample size formula. Now, the big important things that you have to know is when you're reading through a problem that involves minimum sample size, students usually have trouble figuring out what to use for error. And the error is going to be given to you usually by keywords like do a certain estimate and be off by no more than, or get your estimate done within 2% or within $2 or £2 or 2 seconds. So that's how we can identify that the error term is going to be present. So let's go ahead, let's take an example of a question. And take a minute to read through the question if you need to. Okay, so we're going to start just by writing down everything that they've told us. And as we start to affix symbols to these numbers, 95% is going to match with our z value of 1.96. When it comes time to tracking down the 0.15, they've mentioned the 0.15 in the context of be accurate within. So they're trying to communicate the error. They want to estimate the cost of making a pizza, but they don't want to be off by any more than 15 cents. And 0.26 is mentioned as the standard deviation. So that's going to be our sigma symbol. Now, when we load this into our formula, we're going to end up with the values just like so. And our solution is going to be that we need to use a minimum of 11.5 pizzas to meet 95% level of confidence and to be accurate within 15 cents of the true cost.